Hello there, Mr. Sutton here, bringing you the AB Calculus 515 Extra Practice number 3 solutions on integration by substitution with definite integrals. For this one, trying to integrate this from 0 to 2, I notice that we have an inner function whose derivative, something with an x, is also in the function. So let's try and use u substitution on this. I'll start by letting u equal x squared plus 1, so then I can write du equals 2x dx, and then du over 2x equals dx. Now I have to swap out these x values for my limits of integration for u values. So if x equals 0, then u is going to be 0 plus 1, which is just 1. And if x equals 2, then u is going to be 2 squared plus 1, which is 5. So I have the integral then. I can rewrite this as the integral from 1 to 5 of x times the square root of u, and then we have du over 2x instead of dx. X's are going to cancel, and I can rewrite this as u to the 1/2 power, so 1/2 u to the 1/2, kind of interesting there. And now using the reverse power rule for my antiderivative, this bumps up to a 3 over 2, multiplying by 2/3. That's going to be 1/3 u to the 3/2. All of that evaluated from 1 to 5. So I'm going to yank out this 1/3. And let's see here, I'm square rooting and cubing at the same time. So I've got the square root of 5 cubed. And then I'm going to be subtracting the square root of 1 cubed. So let's see here. This is going to be, if we really needed to simplify this, this is 125 square rooted, which is going to be 5 radical 5. This over here is 1. So we have 5 root 5 minus 1. All over 3 if you really wanted to simplify. On this one, I'm trying to do the integral from 0 to radical pi of this stuff here. Now, because I can't really simplify this, I'm going to look at this inner function, and in doing so, I notice that its derivative, which is something with an x, is also in the same problem. So I'm going to try u substitution to start things off. Let me let u equal x squared, so then I can say the derivative of that du is going to be 2x dx. So then du over 2x is the same thing as dx. Now I have to change these limits of integration to u values. So if x equals 0, then u is going to be 0 squared, which also happens to be 0. And if x is radical pi, then u is going to be radical pi squared, which conveniently is just pi. So let's go back now and do some substitution. We have the integral now from 0 to pi, and these are u values now in our limits of integration. I have x times the cosine of u, and instead of dx, I have du over 2x. So the x's are going to cancel. I have 1/2 cosine of u du. Antiderivative of this is going to be 1/2 sine of u. Now we're going to evaluate that from 0 to pi. So yanking out that 1/2, I've got the sine of pi minus the sine of 0. And these are actually both 0, so this whole thing's just going to come out to 0. For this one, trying to find the definite integral from 0 to 1 of this craziness. So one thing I do notice here is that we have this inner function of x squared plus 1, whose derivative with something with an x is up here. So let me try doing substitution on this. I'm going to let u equal x squared plus 1. So then du is going to be 2x dx. And then I can write dx equals du over 2x, because I'm going to have to swap out that dx when I do this. Now for the limits of integration, if x is 0, I can convert that to the u value 0 squared plus 1, which is just 1. And let's say we have an x value of 1 for a limit of integration. Well, now that's going to be 1 squared plus 1, or 2. So going back here and rewriting things in terms of u, I have the integral from 1 to 2 of x over radical u, and then instead of dx, I've got du over 2x. X's are going to cancel. I have a 1/2. I also have a u to the negative 1/2 if I write that with an exponent. Still have that du there. Now using the reverse power rule for my antiderivative, this bumps up to a power of 1/2, and then dividing by that, I'm really multiplying by 2. 2 times this 1/2 right here is going to cancel. So I just have u to the 1/2 power evaluated from 1 to 2. Well, that's not so bad. This is just going to be the square root of 2 minus the square root of 1. Which if I really wanted to, I could simplify to just radical 2 minus 1. For this problem, they want us to rewrite this integral in terms of u. So we have to pick a good u value to represent an inner function here. Now, the only inner function I see is this x cubed plus 8. But the reason I know that I want this to be u is because the derivative of this thing, which has an x squared, is matching this other function here, this other x squared. So it's good when you get the same type of thing when you take the derivative as you have elsewhere in the problem. So let me let u equal x cubed plus 8. So then du, that's going to be 3x squared dx, the derivative of all this. So then I can write du over 3x squared equals dx. Now I also have to convert these x value limits of integration to u values. If x is negative 2, then plugging that in here, that's going to be negative 8 plus 8, which is 0. So that's my u value. And let's say that x has a value of 4. Well, then we have 64 plus 8, so that means that u is going to be 72. All right, substituting back in here, I have the integral from 0 to 72. We have an x squared times a u squared. And instead of dx, I now have du over 3x squared. So just like I predicted, those x squareds are going to cancel out. We just have a 1/3 u squared du integral from 0 to 72. And since they said we didn't have to evaluate this, we can stop right here. On this one, I'm trying to rewrite this integral in terms of u. So let me let this inner function here, 3x cubed plus 3 equal u. And the reason I'm using that is because the derivative of this thing, which involves an x squared, is somewhere else in the problem. So this will interact nicely with the stuff that's going to be left over after I make this substitution. Taking my derivative then, I've got 9x squared dx, and then dividing by 9x squared, we have du over 9x squared equals dx. Now I have to convert the negative 1 and the 0, which are x values, to u values, so I can get a new set of limits of integration. If x is negative 1, then we have 3 times negative 1 cubed plus 3. That's negative 3 plus 3, which is 0. And now if x is itself 0, well, now we have 3 times 0 cubed plus 3, which comes out to 3 actually, 0 plus 3. So I can rewrite this as the integral from 0 to 3 of 18x squared times u squared, and then instead of dx, I've got du over 9x squared. X squareds cancel, 18 over 9 is 2, so we have 2 times the integral from 0 to 3 of u squared du. On this problem, they want me to rewrite this integral in terms of u, so we need to figure out what our inner function is that we want to equal u. I'm going to go with 1 minus x squared for my u value, and the reason I'm doing that is because the derivative of this, something involving an x, is elsewhere in the problem, so that'll interact nicely after I swap things back in for u. So let's see here, we've got du equals, this will be negative 2x dx if I take the derivative of everything there. And then I can write dx equals du over negative 2x. That'll let me swap out that dx there. All right, let's talk about the limits of integration, 0 and 1. If x is 0, because these are x values here, if x is 0, u is going to be 1 minus 0 squared, which is just 1. And if x is 1, well, now we've got 1 minus 1 squared for u, which is 0. Well, that's kind of interesting. So rewriting this in terms of u, we have the integral now from 1 to 0. And then we have x times the square root of u. We have a du over negative 2x instead of dx. X's are going to cancel. I've got negative 1/2. I also have u to the 1/2 if I want to rewrite that, along with the du and the same limits of integration there. And they said I didn't have to evaluate, so I'm going to take them at their word and stop right here. For this problem, we're given some values of some twice differentiable function g in the table up here. They want the value of the integral from 0 to 4 of g prime of x, arctan squared g of x plus 3 dx. Well, this is just a huge mess right here. Now, some things are going to help us out on this problem. One thing that's going to help us out is this is a calculator problem. So at some point, you can use your calculator to get one of these answers. In fact, you're going to have to. Another thing that kind of hurts us at first is the fact that they're throwing in this random g function and g prime, which we don't really have an algebraic equivalent for. If you don't know what g looks like algebraically, you can't use your calculator on it. All we have are these table values. But now here's what's going to help us out. I noticed that I have an inner function here this 2g of x plus 3, an inner function whose derivative is elsewhere in the problem. We have a g prime elsewhere here. So I can actually try using a little substitution in the beginning, and maybe I can clean this up into something that my calculator can handle. So let me start by letting u equal this 2g of x plus 3 term. Well then, du, the derivative, is going to be 2g prime of x dx. And then if I do du over 2g prime, that's going to be the same as dx. Now I also have to swap out my limits of integration. Right now they're x values. I need u values. So if x has a value of 0, then u is going to be 2 times g of 0 plus 3. What's g of 0? Well, looking that up in the table, now this is where the table is actually helpful. G of 0 is 1. So this is 2 times 1 plus 3, which is 5. Next, if x equals 4, u is going to be 2 times g of 4 plus 3. Well, what's g of 4? Looking that up in the table, that's going to be negative 5 halves. So I have 2 times negative 5 over 2. 2's are going to cancel. That's just negative 5. Plus the 3 that's still there, that comes out to negative 2. Rewriting all this now, I have the integral from 5 to negative 2 of, we now have, let's see here, g prime of x, arctan squared of u, and then we have, instead of dx, we're swapping that out for du over 2g prime of x. G primes are going to cancel. This is great news. So we just end up with this integral from 5 to negative 2 of 1/2 arctan squared of u du. Now this is something I can actually plug into my calculator. It still looks kind of nasty, but my calculator doesn't care. It'll do it. So let's do that now. To make this go a little smoother on the calculator, I'm going to put the arctan function, arctan squared function that's in my integrand in my y1, so just so I don't have to mess with doing integral format and all this at the same time. Let me do second tan to get that, and I'll have to use x because that's what my calculator recognizes as the input. And to square this thing, I have to write the squared outside this parentheses. There we go. So now I've got arctan squared in there. Let me quit out, and now let me do math 6 to get my, or actually no, let me do math 9. Math 9 to get my integral function. And let's see here. I want to put a 1/2 in front of that too. So let me insert a 1/2 before I get too far into this. Fancy fraction time. There we go. And let me see. Integral from 5 to negative 2. Great. Let me do alpha trace and then y1. That's where I stored my arctan squared. Let me do dx. Press enter. Hope for the best. This comes out to about negative 3.647. which is going to give us answer choice B. On this problem, they want to know which of these is equivalent to this expression up here. So there's at least one here that we can actually eliminate right off the bat. So this expression here, where we're basically splitting up an integral with multiplication, we know we can't do that. We can split it up with addition, but not multiplication. So D you can eliminate right off the bat. The rest of these seem to involve at least A and B seem to involve some kind of U substitution, so that might be something to think about, integration by substitution. And C, I'm not really sure what they were doing in C. That looks pretty suspicious. Let's go the U substitution route and see if we can get either A or B. And then if we don't get either of those, we'll at least think about C. So in terms of U values, I'm going to pick 2 plus ln of x because I see that the derivative of that, which involves an x, is also somewhere in this problem. So that'll interact nicely with the leftovers after I swap things out for u. So I'll start with u equals 2 plus ln of x. Derivative of that, this 2 is just a constant, so that's 0. Derivative of ln of x is just going to be 1 over x dx. So I can multiply by x to get x du. That's what I can swap out dx for. And now I also need to get u values because what I have right here are x values in my limits of integration. So if x equals 1, u, that's going to be 2 plus the ln of 1. ln of 1 is 0, so that's just going to be 2. And now let's say that x has a value of x to the 6th, or e to the 6th rather. Well, then I'm doing 2 plus ln of e to the 6th. ln of e to the 6th, ln and e actually cancel, giving us just 6. So 2 plus 6 is going to give me 8 for that one. So now I can rewrite this as the integral from 2 to 8, we're going to have 1 over x times u, and instead of dx, we've got x du. X's are going to cancel nicely there, so we just end up with 1 over u du, and 2 and 8 are our limits of integration. These are u values because we swapped out the x values for those. And it looks like we actually already have a match with choice A. Let's do it.